You ever been navigating somewhere new, look down at your phone, and just wonder, how does that little blue dot know exactly where you are? It really does feel like magic. Well, today, we're going to pull back that curtain. We're going to reveal the surprisingly simple math that powers a piece of technology we all use every single day. Alright, let's get into it.
So let's just start with that big question. Seriously, think about it. We're on a planet that's spinning through space, and yet, your phone can pinpoint your location down to just a few feet. How does it take all that complexity and turn it into a simple instruction like, hey, turn left up here?
Well, it's not magic. It's math.
But it's a specific, really powerful kind of math that works like a universal translator for location. The concept is called linear transformations, and it's the secret language that satellites, your phone, and the ground all use to talk to each other.
So to understand how GPS actually works, we need to start with the fundamentals, right?
Exactly. Now, to understand this language, we first need to learn its alphabet. It's a language that's used to tell us where we are. It's a way of describing where things are and how they move using nothing but numbers. And it really all starts with just two basic ideas. First up, we have the vector. The easiest way to think of a vector is just as an arrow. It's got a length, we call it its magnitude, and it points in a specific direction. So on a map, a vector could be your exact position, or it could represent the journey from point A to point B. It's the perfect way to talk about location mathematically. Okay, so if a vector is a location, a matrix is an action. It's this grid of numbers that basically acts like a little machine. You feed a vector into this machine, and it performs a specific operation on it. It changes the vector based on the set of instructions that are coded right into those numbers. And this gets us to the really cool part. These actions, the things these matrix machines do, are called linear transformations. They are the verbs of our math language. They let us move and manipulate our vectors in ways that are totally predictable and incredibly powerful. So now that we understand the tools, what can we actually do with them?
Let's see what that actually looks like. So what can these transformations do? Well, all sorts of things. You can take a vector and stretch it out, or squash it down. You can flip it over a line like a mirror image, or you can spin it around in a circle. These are the basic geometric moves that let us reshape space using math. Let's look at our first example, projection. This one's super intuitive. Just imagine a really bright light shining straight down from the sky. The shadow that an object or our vector casts onto the ground, that's its projection. It's like we're squashing all its 3D information down onto one flat line. And this is the code for that action. I know, it just looks like a bunch of fractions, but this matrix is the recipe for creating that shadow effect. When you multiply any vector by this matrix, what you get on the other side is its perfect projection. This is the mathematical instruction for squish. Okay, next up is reflection. And it's exactly what it sounds like. You take a vector and you flip it to its perfect mirror image across a line. It stays the same distance away, just on the opposite side. Simple as that. And you guessed it, that action has its own unique code. This matrix right here is the specific instruction for reflect. And notice how the numbers are totally different from the last one? That's the big idea here. Every single unique action has its own unique matrix code. Now, we've covered projection and reflection, but there's one more transformation that's absolutely critical for GPS. Right. The last one we're going to look at, and this is the most important one for solving our GPS mystery, is rotation. This is the action of taking a vector and just spinning it around the center by a certain angle, without making it any longer or shorter. And this is where things get seriously powerful. This matrix uses basic trigonometry, sine and cosine, to do all the hard work for you. You just decide how many degrees you want to rotate, you plug that angle in for theta, and this incredible little machine calculates the vector's new coordinates perfectly. It's amazing. Okay, quick recap. We've got vectors as locations and matrices as actions, like projection, reflection, and especially rotation. Now it's time to connect all these dots and get back to that little blue dot on your phone screen. So I think everyone's wondering, how does this all connect to GPS?
Great question. So how does rotating an arrow on a piece of paper help a satellite way up in space find your car on a highway? What is the actual connection here? Well, it all comes down to perspective. See, the biggest challenge for any GPS system is that there's no single map of the world. There are multiple ways of looking at your position, and your phone needs to be fluent in all of them. It has to constantly translate your location from one point of view to another. Let's break them down real quick. First, there's NED, or northeast down. That's your local view right where you're standing. Then there's ECEF, which is a view from the exact center of the Earth. And finally, there's CIRS, which is the big picture view that remembers the entire Earth is spinning through space. Your phone has to juggle all three of these views at the same time. So the big question is, how does your phone translate between all these different perspectives?
Well, here's where everything comes together. So how does it translate between these different points of view? How does it get from that Earth-centered map to your local North is that way map? You already know the answer. It uses a rotation, and not just any rotation, a master rotation matrix built for this exact job. And here it is, the direction cosine matrix, or DCM. Now, I know that looks intense, but don't get thrown by it. Look closer. See all those sines and cosines? This is just a superpowered 3D version of that simple rotation matrix we saw a minute ago. It's just a combination of rotations designed to translate between different viewpoints on a spinning globe. This is the master translator. This is the engine that makes GPS work. So we've solved the mystery of how GPS works.
We have. So we've kind of solved the mystery. But what's the big takeaway? Why does understanding any of this actually matter to you, especially if you happen to be a student learning this kind of math right now? Here's the most important part of this whole thing. This kind of abstract math, it's not just a subject you have to pass in school. It's not just problems in a textbook. It is the literal code, the fundamental language that we use to design and build the modern world all around us. That incredible piece of technology in your pocket? It's not unknowable magic. It's just a series of logical instructions. The very same linear transformations we just walked through. This isn't some secret knowledge for geniuses. It's something you can understand, something you can master, and something you can one day use to build things we haven't even dreamed of yet. So the next time you're in class working through a matrix problem, don't just see a grid of numbers. See a set of instructions. See a rotation, a reflection, a powerful tool for translation. See the engine behind GPS.
This magic? It's just math.
And the only real question left is, what will you build with it?